Hey folks, thanks so much for stopping by. Um, so this is the fourth uh, in the lecture series for the Artin reading group, and sorry, dealing with something on the back end, but yeah. So I want to pick up where we left off, talking about quotient groups. We mentioned quotients, and specifically their in the context of modular arithmetic previously. And so we'll pick back up on those threads. But I don't think that's going to take the whole time. Of course, feel free to ask me questions so that it does. But in the likely event that we have some extra time at the end, I have some material prepared for the beginning of chapter 3 on vector spaces as well. So let's get started. Of course, feel free to post any questions in the Discord chat, or unmute yourself and ask. Those are both valid. If you're hanging out in Twitch, I'm also monitoring that chat as well, so should be able to catch you no matter uh, how you want to get your feedback. So I'm going to start off with this big example that both Goose and Run talked about, which was so this modular arithmetic. And I'm not going to do a very serious treatment of this, but I just want to highlight one particular thing that's going to be useful as we go forward. Um, so we'll stick to a very concrete example. So the group, we'll say our big group is the integers, and we're going to pick a subgroup, and all subgroups look like some, multiples of some number. So here we're going to pick that number to be 3. Um, and the picture that you should have in mind is something like this. Let's try that again. So we pick, the integers sort of have this come with this natural order. So it starts with 0, or that should be positive, please. Of course, when I say starts with 0, I mean I'm going to start with 0, but it begins closer to negative infinity. Um, so, um, and we're going to highlight the group here. Uh, let's make that thicker. Can we get away with something that thick? Maybe. We'll see. Um, okay, so we'll put the group in blue. And then the whole story behind modular arithmetic is that you can somehow I am sharing my screen on Discord using the camera critter Archdomina. Thank you for asking, but yeah, hopefully it should be visible. Do let me know though. Um, so this is a subgroup, and in particular, being a subgroup, it is a coset. It's the special coset that contains the identity element. But there are also 2 other cosets. So there's 2 other cosets. Oops, that should be new. 2 other cosets, which I think I'll label in red and green. So we got to make some choice here. Let's choose the coset containing 1 to be red, and the coset containing 2 to be green. So this is sort of the story, and of course this coloring extends out forever. But there's this miracle that happens, which is that if we want to add some numbers together, right? Okay, so I don't know, 2 plus 1 is equal to 3. Hopefully not news. So 2 is green, 1 is red, and 3 is blue. So this we can forget about the numbers here, and I'm glad. Seems like we had some success with folks finding the picture video. So yeah, so we could try the same, just like forgetting about the numbers and just put the colors down here. Like what happens if you add a green and a red together? Well, this could get pretty wild. Could take the green to be 5 and the red to be -2. That's also 3, so maybe that wasn't the best choice, but okay. Yeah, let's make a different choice here. So then what, -8, that's gonna be red as well. Um, and so this is equal to -3. And this ends up being blue also. So we seem to have this equation that doesn't really care very much at all about the numbers involved, which are so schematically we seem to have that if you take a green number and you add it to a red number, then you get a blue number. And this is more than it just seems this way. We went through some arguments in the last 2 lectures. Thank you, Ren and Goose, uh, to for sort of seeing exactly why this holds. And of course, it's also in the book and in the lectures. So, or sorry, in the gross lectures. Um, but we want to sort of build on this idea. Which is yeah. So we could indeed uh, the colors. Okay, when I say colors, of course, I mean cosets have their own group structure that's compatible with the structure on Z. Right. Now, I want to emphasize that this is not at all a um, this is not at all like something that you should expect. Uh, so I want to go through at least one example to talk about what could happen here. Um, and so there's some text from Artin that we'll come back to in a minute, but um, so a non-example that's useful to have in mind is that what if you have the group to be something like S3 and subgroup, I want a subgroup to be well, something like this. Okay, remember S3 is the number, or excuse me, is the group of permutations on 3 letters, and so I'm saying, what if we just look at the element that swaps the first 2 things in the list? Of course, that is a transposition. So if you multiply it by itself, you swap them and then you swap them again, you get back to the identity. So this thing right here is a subgroup, and it's a perfectly good subgroup. So let's try to draw sort of a similar picture. The nice thing about S3 is that it's small, right? So we might have the identity and 1, 2, and yeah, maybe I should have kept my coloring scheme. So we'll highlight that subgroup in blue. But there are some more elements in S3, of course. There's maybe the element that swaps 1 and 3 instead of 1 and 2. And so if we think about, sorry, that's also unreadable. Let's try again. And so if we think about what the coset containing 1, 3 is going to look like, well, of course, if you multiply by the identity, you get back itself. Okay, so that's not so interesting. But if you multiply by the non-trivial element of this subgroup, 1, 2, um, then, okay, so I don't want to spend too much time reminding us how permutation notation works, but so this is, well, okay, I'll just say that um, this 1 gets sent to 2, and then 2, nothing happens to 2 over here, so that's going to be 1 goes to 2. But now 2 goes to 1 over on the right-hand side, and then 1 goes to 3, which means that 2 overall goes to 3. And similarly, 3, nothing happens to it over on the right side, but then it gets sent to 1 over on the left side, and so goes back. Okay, so that means that the other element in this coset is going to be 1, 2, 3. We got to pick a color for it. Might as well be green. Confirming Anders' suspicion that green and red makes this fairly ugly brown color, but okay. Okay, and so then there's only 2 more elements left in S3. So let's pick one of them. I think we haven't used 2, 3 yet. Okay, and we could check, but we sort of know by the way that cosets work that the last element is going to have to be in this coset as well, and the last element is 1, 3, 2. Okay, so perfectly good setup. Nothing is out of the ordinary so far. This is just a group, a subgroup, the relevant cosets. Um, Life is good. But let's try to do this color stuff again. So for instance, if I try multiplying something like, let's try 1, 3 times 2, 3. Okay, so we'll go a little bit faster through this multiplication. Uh, 2 goes to 3 goes to, or excuse me, let me start with 1. 1 does nothing over here, and then it gets sent to 3 on the left. 3 gets sent to 2 on the right, and then 2, nothing happens to it on the left, so there's a 2, and that's going to close. So this is putting the colors in there. This was green multiplied by yellow is equal to yellow. And already that should start to be concerning to you, right? So because what this means is that if there was going to be a group structure here, well, the only way that you can multiply 2 group elements together and get the same group element back, and remember, if we forget about the actual permutations here, we just focus on the colors, then yeah, that's really what's happening, right? Green times yellow gets you yellow back. That means that green would have to be the identity. Oops. So if this green would be the identity. Okay, but we don't think that green should be the identity. We think that blue should be the identity because blue, after all, is the coset that contains the identity element. Right? And so indeed, we can finish off this to see something really go wrong. And I got to remember, one of these it will not go wrong. One of them it will. I think that it's think it's 1, 2, 3 times 2, 3. So this again is green times yellow. But when you multiply these together, 1 gets sent to 2, 2 gets sent to 3, which gets sent to 1, and 3 gets sent to 2, which gets sent to 3. Okay. And so this is blue. So this is now genuinely a problem, right? It's not just sort of suggestive of a problem. This really is a problem because supposedly green times yellow was supposed to be yellow, but now green times yellow is blue. Like the something is going wrong here. I want to linger on this for just a second. The conclusion here is that not only do we not have a group structure, but in fact we don't even have an operation, right? Um, so the colors don't have like unique products in the sense that what I said before, green times yellow equals uh, yellow and blue. So of course, what we want to do is we want to think about, what's happening, in this example that's bad, right? Something is happening that's that's different from what was happening in the modular case, the modular arithmetic case. And the first thing you might say is, well, this is probably because, oh yeah, sorry, in the Discord chat, Pinata has a good uh, video posted. I think I've seen this one before. If these sort of cycle notation computations were not familiar to you, um, or just like uncomfortable, because I think we did, but I definitely would encourage you to go take a look at that. So I'm bearing the lead here. Yeah, definitely, Pinata. We'd love to see that in discussion as well. I'm bearing the lead here, which is a little bit silly because it's literally on the screen already, right? The It's very suggestive that this we're probably going to be talking about normal subgroups. um, so this was some notation that was introduced before. We for a single coset we can say like an element times the subgroup. But if we want to talk about all of the cosets at once, we want to think about the family containing all of the cosets. And here I just use family as a synonym for set, so I don't have to say sets of sets of sets. Okay, a family of cosets. Um, then there's two notations we like. This quotient notation, which is sort of suggestive, and we'll have some things to say about that down the road. Um, But also, perhaps slightly less suggestive notation is this G bar, which is really handy. You see this very often in the modular arithmetic setting. I'm going to try to avoid it in this lecture just because I like to remember the difference between elements and sets, right, and cosets. So, but if you don't want to emphasize that subgroup or the coset structure as much, then you can sort of use that bar to hide the subgroup. So it's going to turn out that normal, yeah, well-defined is the English term for this. So do I have a spare color? Not really. Let me pick one from the palette. So this is not well defined. So we need something like the following, right? If I'm really going to tell you that normal subgroups are making the magic happen, um, then we need something like this. We need to know that there is a well-defined operation, right? Uh, so real quick, what is this lemma saying? Okay, so it's saying that there's an equality of sets, right? Both of these two things here are sets. Um, the set on the left is every group element that can be written in the form a n times b n, where those n's can be different. And then this thing on the right is saying, and hopefully that shows up. Do let me know if that color isn't good, but um, this is a times b times n for any n inside of that subgroup. Okay. So one thing that I want to highlight here is that there's one of these directions is very obvious. So it's written as an equality, but somehow it's only one of the inclusions that we care about. So the obvious direction is this direction. So this is sort of straightforward. And why is it straightforward? Well, because uh, look at this thing here. Since n is a subgroup, in particular, it contains the identity. So if we set that to be the identity, then everything in the right-hand side looks like uh, a times b times n2. Okay, and swap n for n2, life is good. So somehow it's the other direction. The fact that when you take two cosets and you multiply them together, you could get more than the coset you expect. But if it's normal, you don't. Right? If it's normal, we're going to uh, only get that single coset and nothing from anywhere else. I'm going to pause here, see some typing in case there are questions, because this is a good thing to understand. Sort of, it's really the foundation for everything that we're going to do in groups for the rest of this lecture. Okay, also a question in Twitch, so let's might take a moment for them to come in. This question's more about the course structure. Yeah, there will be some ring theory in the future. Uh, while the question comes in, I will say that the proof is going to be pretty short. Okay, so we could prove this very directly, but in fact, I'm not even going to do that much by sort of chasing around elements, because it was essentially already done for us in toward the end of the lecture by Goose. They presented a lemma from the text that ends up doing all of the real work for us. So push that now. So here's the magic statement. Oh, it's big. So Goose proved this. Is that readable? I feel like that's a little rough. One more time. One more time. Okay, so in last lecture. Goose proved this. That normal subgroups, uh, yeah, Vin, that's exactly correct. So in the uh, in the chat right now, you can see a slightly more carefully written explanation of the easy half of this theorem. So last lecture, Goose was proving this, right? So it says that if you have a normal subgroup, so we are using the normality for this this thing, then you have left cosets are the same as right cosets. And not only that, but you actually know which left coset corresponds to which right coset is sort of the one you expect, right? If you multiply by an element on the left, excuse me, if you multiply an element by the group on the left, that's the same as multiplying the element by the group on the right. I think I got the hands wrong there, but also that reminds me. Okay. Yeah. So I claim we're done. This thing that Goose did essentially resolves the entire problem. Why? Well, let's try to start writing things down. So we need to start with a n times bn. Okay. Well, you can't stop me from writing that like this because anything that is an times bn, uh, an1 times bn2 is the same thing as an element that is a times n1b times n2. Okay, nothing to prove here. And now the magic. Because of proposition 6.8, we can replace that nb times by bn. And start moving stuff around. This is AB. Well, keep the colors. Why not? Times n. There should definitely be a b there, not an n. Okay, let's try that. um, and then this. So it looks like we're pretty close, right? We just have too many n's here, but remember that n is a subgroup, right? And so that means it's closed under multiplication. So if I take any two elements in n and I multiply them together, I get something else in n. And conversely, I can write anything in n as a product of two elements in n. So, no, we'll just leave it like that. Okay, and we're done. Yes. And as Anders, the hiragana person in chat mentions, this is actually I was about to say exactly what Violet says. You could in fact take 6.18 as the definition of a normal subgroup, and some texts do choose to prove this. Excuse me, do choose to make that choice. But Artin makes the choice that normal means. So Artin says that normal n means or is defined by Gn. G inverse is equal to n for all G. Saved indeed. Just checking that there weren't any other questions that I missed. but I think we're good. All right, so this 618 is really the workhorse of 10.1, and 10.1 is going to be the workhorse of everything else. So what does 10.1 really say? It says that we do have the dream that was not achieved by our symmetric group example from before. Um, Back here, we had this problem with unique products, but because uh, of this lemma right here, we know that the products are like the products of cosets are well defined and they are what you expect them to be. So let me write that down. So this lemma says that there is an operation, or maybe I should say a law of composition, which is, remember, just a pretentious way to write a multiplication that takes a coset. Remember, this is the set of all cosets, the family of all cosets, and another coset, and spits out a third coset, um, in the way that you expect. AH times BH uh, is equal to ABH. Yeah, and I guess I missed the most important part of this statement, which is that if H is normal. One can argue that the um, the converse is also true. That if the group is not normal, you are never going to have a law of composition. So uh, Artin does this. I can't remember if Prof. Gross does this, but um, such as it is. Now, this doesn't prove that there's a group structure. It just proves that there's a law of composition. Remember, we have to satisfy all these axioms. So it could be a group. If it satisfies the axioms. Uh, for right now, I'm just going to say it does. Um, and I'll give you some idea about sort of the important bits there. Um, right. So the identity. What's the identity? Well, that should be the element that contains the um. Good. Okay, I think I'm good. um, should be the thing that contains the identity element. So that's EH, right, or just H. And then what about inverses? Well, that's going to be, I want the inverse of this. Well, you'd probably guess it. It's going to be the inverse of H. Or excuse me, the inverse of A. The coset corresponding to the inverse of A. So in some sense, the reason why it's a group is just because because we have this very, very strong compatibility. It's not just that we have some random law of composition on the set of cosets. It's it's very, very compatible with the group structure upstairs, right? And so the group structure upstairs somehow comes down, right, and imposes a group structure on this collection of cosets. So this is formalized by Artin in this proposition. So with the law of composition defined as above, that is as in 10.1, then the set of cosets, which you can write in either way, uh, Gn or G bar is a group. But Artin actually describes it in a slightly different way. Um, yes, and I should say about that, because this confused me for a while. I have been calling these quotient groups the entire time, but there some texts prefer the term factor group. So this is a quotient group, which is sort of annoying, right? Uh, because I think about quotients and factors as being sort of opposite kinds of objects, but unfortunately, both terminologies are standard. Okay, but what I was getting at is that the Artin like has this additional kind of structure going on here. He also says that not just that you have this group, but in fact this group arises from a homomorphism. Uh, right, and in fact, I mean, just because we can, we say that we know the kernel. And so that homomorphism is precisely this thing going on in 10.4. And just to put a really fine point on it, uh, this is precisely the sort of thing that we were calling the coloring map, right? So just write that out. Sorry, G. So if G is equal to Z, and H is equal to, well, I guess I should maybe call it N after all this time, is equal to 3, or 3Z, then G mod N is equal to Z mod 3Z. And so pi is this quotient. Coloring map, because remember what all of those colors were doing is they were just telling us about cosets. So so sorry, words. So for instance, oh, do I remember what the coloring scheme was? I think so. So for instance, I mean, example inside of an example, pi of 2. Oh, goodness. Pi of 2 is equal to, well, it's equal to 2 plus 3z. Okay. Y plus, because this plus here is for the group law on Z. And I thought I was going to say something. All right. Yeah. And remember that this is the set 2, 5, 8, as well as -1, -4. Right. So all of the things that we would have colored green in that picture from before. Assuming that I remembered my colors correctly. Let's see. Yeah. And this is fully general, is the point. You don't have to, um, we've focused on this very specific example, but it works for any group. Um, Maybe the only thing. Oh, sorry. Yeah, I should say. What's there to prove? Okay, it seems like everything is proven already. So I won't prove it because it's first of all not very hard, and second of all, uh, it takes longer than you want to. Uh, so first of all, of course, we need to check that the kernel is what we think it is. But more to the point, just because you have a map between two groups doesn't mean that that map is a homomorphism, right? Uh, so far, all we have is that pi goes between groups. Need to check, for instance, that pi of 0 is equal to the identity element over there, and pi. Can we still see it down there? Yeah. Okay. Being a little sloppy here just because we're not actually going to do it, but you still need to check that it's a homomorphism. The bop emoji? Okay. Right. I don't know why I have this slide in again. Let's keep going. So one of the kind of fun things about this, the phrasing it the way that Artin does, is that it allows you to see this converse to the statement that we had earlier. So way back in Ron's lecture, and I'm sorry if I'm saying your name incorrectly, um, but Ron argued that the kernel, right, of a homomorphism is a normal subgroup because we were like, okay, we've got this weird definition. Is there anything that actually is a normal subgroup? And yes, homomorphisms give you a way to find those things. Okay, so oops. Hmm. But what we now see, this because of all of this work that we've done, is that in fact these are the only examples. Not only can you uh, get a normal subgroup by looking at the kernel of a homomorphism, but in fact every homomorphism, every normal subgroup has an associated homomorphism that it's the kernel of. Why? Well, because so proof. Uh, if n is normal, then n is the kernel of the map, this quotient map, sending G to G mod n. Mhm. So this is yet another equivalent definition of what a normal subgroup is, right? So again, I think when you see this for the first time, the introduction to this definition of this weird conjugacy nonsense, you're like, why are we doing this? And the answer is just because it keeps showing up over and over and over and over again. It's also left cosets or right cosets. It's also precisely the kernels of homomorphisms. It's really a remarkably natural definition from a lot of different angles. So I'm happy to take questions on this, but I'm gonna move forward while you type in. and we're going to take a small detour. Now, I'm not going to spend a lot of time talking about product groups. Artin has an entire section on this. But I want to do this just to give you at least one more example, sort of what the uh, I, maybe because I think it's a good transition between like this generalized notion of these quotient maps and what's coming up next, which is the first isomorphism theorem. So there's this whole structure, program in group theory, I guess, to take smaller groups and turn them into larger groups. And as Benedict Gross says in the lectures, you have to be careful about what that means. This can be, just because you know the two factors doesn't mean sort of the thing that they produce together. You need a lot more information than that. But um, one sort of the most straightforward possible way of doing it is just to say like, okay, if I have two groups here, I'm going to create pairs where in uh, the first coordinate of the pair, we put elements from G. In the second coordinate of the pair, we put elements from G prime, and you multiply them together by just multiplying them together component-wise. Very natural. So at this point, Artin draws a certain picture, a picture that you can show to, and I'm going to write G cross H, that you can show to any category theorist to instantly KO them, um, which is this. So if you are sort of categorically inclined, you don't really want to draw the second half of this picture. Uh, and I will say really nothing more about it than that, except that this side of the picture is sort of the side we're going to focus on anyway, so we'll just leave it there. But what are these things? These things are homomorphisms, and they act in sort of the natural way, right? So for instance, what is this one? Well, that is the homomorphism that sends a group element to uh, G comma 1. And I guess when I say 1, maybe E, the identity element in H. Right? So there's a copy of G sitting inside of G cross H because you just forget that H is doing anything and just keep it at the identity all the time, and everything goes well. Okay, and then conversely, like what's this? What's actually I want to do this one. So what is this? Well, you have to start with an arbitrary element in G cross H. Looks like that. But I don't want to have an H at the end, so let's just forget about it. Right? Sure. Okay, so this half of the picture is sometimes called the inclusions because they include the group into the bigger group. And this half are called the projections because we project down onto each of the factors. This has a very, very concrete meaning. Like it really looks like a projection if you take G and H to be the real numbers. So if G and H are both real numbers with addition, then you can literally draw what it looks like. This is G, this is H. And if I pick some random elements in here, and I think about what this projection map is doing, well, it's just saying I don't care how high they are. I don't care where they are in H. I just want to know what's going on here. project, that one goes to that group element, that one also goes to that group element. So, to the x-axis. Uh, yeah, this is being, sorry, for folks who are asking in Twitch, because I see a couple of comments, this is all happening over in the simple group Discord. You can type !simple in the chat and make your way over here if you want to be part of that conversation. So what I want to note here is that the projection map, yeah, no, let me call it projection. So this is the action of P. Maybe I'll say P G. Here. And if we think about what the kernel of P is, the kernel of P is all elements in GH such that G is equal to the identity element, right? Because that's what you, because this over here on the left-hand side is what you get when you apply PG. You just forget about H. And so this is, if we want to be careful, we'd write 1 cross H, but it's clearly H, right? Um, you know, it's not literally equal to H because it is technically a set of ordered pairs, and H is not a set of ordered pairs, but it is functionally H, right? The second element of the ordered pair is always the identity, and so it doesn't contribute anything to the group structure. And so if we take this in light of our previous theorem, what it says, so in of the big theorem, I can't remember the number, 10.5. This says an equation that looks very, very natural when you write it down this way, but it only looks natural because the notation is very good. Which is that if you take the product group, take a product of two groups, and you quotient out by groups. Okay, and I'll be careful now, really. 1 cross H. Then this is isomorphic to G. So this is one reason why the term quotient is used, right? It's because it is sort of an inverse to the direct product. When I say sort of, what I mean precisely there is that um, the blue, statement in blue is true, right? It is that if you take a product and then take a quotient, you get the original. It is not true that if you take a quotient and then take the product, you get the original. So it's only like a one-way inverse. Um, but I don't know if this was the original motivation for this definition, but or if you mean for this terminology, but it is like a very convenient thing to have in your back pocket. And what sends it that way? Well, it's the because of this red example. The red example says that PG does this, but the theory tells us that pi does this, right? That canonical quotient map. Um, these two maps are the same, right? Not too hard to convince yourself of this. So this is sort of concretely, like, this is another example that you should have in mind aside from this coloring map. Like, what do these quotients look like? And so now we're gonna finish off. We're gonna take our stretch break first, but when we come back, we're gonna uh, punch the highlight for this the the theoretical side of this group theory chapter, which is that it's not just that the canonical quotient is a quotient, but in some sense, every homomorphism is more or less a quotient. There's a small asterisk that you need to add to that, but somehow these pies, these canonical maps, are the only game in town, up to just changing your perspective a little bit. And again, we'll come right back to that, but let's stand up and take 10 minutes break. We'll start it up again at 10 past the hour. All right, folks, we are going to get started. Again, we do, well, or get restarted, of course. Uh, we do welcome those questions, if you've got them. So, as promised, it's now time to take this intuition and move on to our last result from this section, which is the first isomorphism theorem. There are a couple of more isomorphism theorems. If you're interested in them, you can go look them up on Wikipedia. I don't think I would make quite as strong of a claim as Artin does. It's like they're not really that important. I think they're kind of important, but um, they're we're not going to use them in any substantial way for a while. Certainly not until we get um, past the vector space stuff. It is, and they're a little esoteric, I guess. And maybe I should say they're a little bit theoretical. So I don't think that like having these in your back pocket is gonna like bust out a good solution to one of these homework exercises or anything. I think it's just if you want to know, you can know. But this one is kind of a big deal. Um, so the claim here is that is sort of a converse to right. Uh, Sort of converse to this big theorem that we had before, that if you have a quotient group, then you can understand that as coming from a homomorphism, right? A surjective homomorphism even. And so the first isomorphism theorem says, to what extent can you turn that around? If I have a surjective homomorphism, to what extent can I say that that comes from a quotient group? Uh, and the answer turns out to be sort of in a very strong sense, you can say this. So you hand me any surjective homomorphism at all, um, and I sit there and compute the kernel of that. So you handed me this. I went in there and I computed the kernel. Because it is the kernel of since it's a kernel, it's necessarily normal. Um, this is an important piece that isn't being said, but again was shown to us by um, 2 weeks ago by Ren. So because it's normal, we can talk about the quotient group G mod n, and it says that in fact G mod n is isomorphic to the target. Right? This G prime. Let's keep it visible. That'd be good. Is that G prime? And indeed, you can say precisely the um, what this isomorphism is. Um, it needs to begin by acting on a coset. So it needs to take in a coset. So that's take in a coset. So again, remember you can write it in that bar notation as well. And it needs to spit out something. Well, it needs to spit out phi of A. And what is A? A is an element that you choose to represent the group, or excuse me, to represent the coset. So this isomorphism theorem is really the first place that we have a serious issue coming up with making sure that our objects are well defined. And this happens all of the time when you're working with quotient objects. And one of the other ways to think about what the first isomorphism theorem says, and I think this is the way that Artin prefers, is it says that anything that is a quotient group, you can write it as something that's not a quotient group, right? If you can find the correct homomorphism. And the disadvantage to working with quotient groups is that the elements of a quotient group are sets. And so if you want to figure out where that set is going, then often the way that you want to do it is you want to pick an element in the set, and you know something about what happens to that element. Because it's easier to work with elements than it is to work with sort of all of these elements at once. But the problem is that you might make a choice of elements in a coset, and I might make a choice of elements in the coset. It's exactly the same problem we were dealing with the two different ways of getting reds and blues from earlier, right? Uh, we got to make sure that that map is well defined. You got to make sure that no matter what you pick, what I pick, when we pass it through the homomorphism, we're going to get the same thing. And that's not at all clear, right, from the way it's written down here. Um, if I chose, if B happens to be an AM, that means that A is equal to B. But Y is phi of A equal to phi of B. And I think that I haven't really quite posed the question correctly yet. So we need that this is equal to this. But if you ask how these things are defined, then that means that these, phi of A should act as the same as phi of B. It's not at all clear, right? It's not at all clear that is the case. So this, I think, I didn't prepare this proof beforehand, so I will say up front that I might have to bail out, but don't think it should be too awful. And I think it's going to come down to sort of the same kind of argument that we use to prove, excuse me, that Goose used to prove this big lemma way back at the beginning that was helping us out through our definition of quotient groups. So the plan is that phi of A times phi of B. Well, phi is a homomorphism, and that's just given to us, right? We're not like assuming, we're not constructing anything. We're saying, hey, we know this is a homomorphism, so you can't stop me from writing this. Okay. Uh, and what I want to do, shoot, no, sorry. Um, and sorry, that this, let's be clear about this. So if we could show that this was equal to the identity, then we could multiply this equation on both sides by phi of b, and we would get what we want. So suffices to show that phi of a times phi of b inverse is equal to e by multiplying this on both sides. So what we're saying is that we are hoping that this, we're hoping that this element, a b inverse, so now it suffices to show that a b inverse is in the kernel of phi. Because that's what it means to be in the kernel of phi, is that when you apply phi to it, you get the identity. And if we could get this, then we can multiply on both sides by phi of b, and everything sort of, backwards, backwards, backwards. Okay. Well, what you know from way back up here is that it's not that any two elements need to multiply together to be, not that any two elements need to give you the same answer when you send them through phi bar, but it's precisely that the two elements need to be the same if they represent the same coset. So we can use this uh, using that b equals a times n for some n is an n. That means that, okay, this is some, I made life hard for myself with these notational choices, but let's do it. Let's take, I don't want to fit this all into the bottom here. Let me go back up here. So we want to show that a b inverse, yeah, a b inverse is in the kernel of phi, and we're using that a equals bn for some n in n. So what I want to get is I want to show that that AB inverse. I want to manipulate this equation so it looks like an AB inverse. And I think that that is going to be somewhat annoying, actually. But yes, no. But here's what we can do. We can multiply both sides by B inverse. And then this, by the definition of normality, this is inside of n, right? Since n is normal, we have B and B inverse is inside of n. Definitely not true for any subgroup, but true for a normal subgroup. And now I bet, I've forgotten the definition, but I bet n was supposed to be the kernel of phi. Let me check. Yeah, by construction, n is the kernel of phi. So we write that. So the conclusion from all of this is, so we have that AB inverse is the kernel of phi as desired. Okay. Yeah, like I said, I probably should have done a little bit more work to clean up that presentation. But what we've ultimately shown is that, so after all of these suffices tos, we conclude that because of what we just did, we've shown that AB is in the kernel, and therefore we've shown that this is true, and therefore we've shown that this is true, and therefore the conclusion is that this map phi bar is well defined. In the lemma AN/BN, you have B is in AN. I hope not. I hope that's not true, but let me check. I'm not restricting myself to only choosing A's and B's here. B that right. So, sorry. So for those who are not following along at home, in chat the comment was that from this lemma we have that B is in A. And I do not think this is true. So perhaps I'm misunderstanding what you're saying. But oh no, maybe what you're saying is that assuming that we have B is in A, right? Uh, so we can use this lemma. Yeah, that I think that makes more sense. Right. In the proof of the isomorphism theorem, we have that B is in AN. So the claim is we should just use the lemma, right? Instead of trying to use the same idea, we should just use the lemma itself. And I trust you. B inverse is going to be right because it's normal. Bn is equal to an, so yeah. Okay. I'd have to think a little bit about how to write that down in a way that would convince me, but I think I see the idea and I agree. This should work. So for those who are not following along, in the Discord chat, Vin has written down an alternate argument for how to prove this part of the first isomorphism, the well-definedness, which turns out to be the only interesting part. Um, the rest is pretty straightforward. But yeah, so there's this alternate lemma that more directly uses. There's this alternate proof that more directly uses this lemma, which is sort of in the spirit of what we were doing in the first half. All right. Yeah, thank you so much. So I guess the last thing that I want to say is, okay, this tells you that every surjective group homomorphism, so stepping back from the details, we spent a little while getting bogged down in the proof, and part of that was on me. So thank you for your patience there. But pulling back to what this thing is going to tell us, like what do we learn from this? We learn that anytime you have a surjective homomorphism, that is uh, that is functionally the same thing as a quotient, right? Because you can the sort of diagrammatic picture here is, I don't know what other kinds of diagrams there would be, but diagram here is that if phi sends g to g prime, then we know that pi sends G to Gn, and where I'm using the same n as in the theorem statement. And so the claim is that these two things here are isomorphic. So in fact, the action of phi looks exactly like the action of pi, except that we relabeled the group elements. We relabeled the cosets to look like things in G prime, but somehow the structure underlying them is precisely the same. Now, this doesn't cover every group homomorphism. This only covers surjective group homomorphisms. But as was mentioned, I believe this was by Goose, this is not such a problem, right? If your map is not surjective for non-maps, that sends G into G prime. Well, you can restrict the codomain. So you can say, well, forget about the rest of G prime. I just want to look at the things in G prime that are actually being hit by something in G. So the picture here is G prime is this. Or sorry, that's not how I want to draw this picture. So phi is acting, and it might not, if it's not surjective, it's not going to hit everything in G prime. But it is going to still hit this piece here. We know that this image is a subgroup of G prime. Not just a subset, right? But it's really a group in and of itself, and it is a subgroup. And the first isomorphism theorem applies to this. So I might not be able to represent the entire codomain as looking like cosets from the original group, but I can represent sort of the only piece of the codomain that matters from the perspective of this map as coming from these cosets. Yes. Now, what Pinata is saying in the chat is something that's mirrored by Prof. Gross in the lectures, which is that there's sort of a bigger story here, that about short exact sequences, and that's something that I'm not going to say, or I guess these would be long exact sequences or longer exact sequences. But I'm going to leave that comment sort of at that phase for now. This is a moment of transition. In the last 25 minutes, we'll be saying a few things about vector spaces. So I want to make sure that if there are any last comments or questions about the group stuff, that we get those in the air, on the table, whatever metaphor is appropriate. Checking over on Twitch as well. So I'm not currently seeing anything, but if you are in the middle of typing, please keep doing so. More than happy to come back. I would rather that everybody feels good about what we've done so far than to keep sprinting ahead into vector space stuff. But as it stands right now, I will begin. So if you're like me, you learned about vectors from a physics class. We were talking about force diagrams and stuff like this. If that is your situation, then you're probably familiar with vectors as looking something like this, which is so we take the coordinates because we're coming from physics. We are thinking about physical space, which looks three-dimensional at least. Okay. Uh, Weird things, perhaps in the modern era aside. Um, so we can describe any point in space by these three coordinates. Pick your favorite starting point, pick a set of axes, and then describe how far you have to go this way, how far you have to go this way, and how far you have to go that way. Okay. Uh, Now this, I guess I should draw the thing that I just said. I'm actually going to prefer to do this. And so a generic vector here is going to look something like that, where you could try projecting it down into the xy plane, and then it has some kind of it has coordinates down there as well. And that's positive, 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 but in general, these things can look a little strange. So like this. So there's a couple of things that you can do with this structure, sort of very naturally, that behaves well with this geometric picture. So one thing you can do is we can scale these vectors. So in other words, just keep the same direction, uh, but perhaps make it a little bit longer or a little bit shorter. And we can also add these vectors together. And that, intuitively, you might not quite see the geometry there, but I'm sure that at this point in your life, all of you have become acquainted with this parallelogram rule, right? That the right thing to do is to take your vector, move it from being at the origin and put it at the head of the other vector. And it doesn't matter which direction you do this. Of course, sorry, it matters which direction, but it doesn't matter whether you take the blue and move it to the head of the red, or the red and you move it to the head of the blue. Both things will get you to the same point. We call that the sum. And if you had a very good physics teacher, they probably mentioned that even though sort of R3 is the thing that makes sense for the space for describing the space around us, mathematically there's no reason to stop, right? Adding things together is a very simple operation. You just do it component-wise. And so I'm going to aggressively challenge my color drawing skills right now. And you probably don't even need me to fill the rest in, but I will. If you have x, y, and z, and you have x prime, y prime, and z prime, then you just add them together component by component. Red y should not be primed. So this operation is very algebraic. Right? This operation is algebraic, even though it has geometric meaning. So we don't, or maybe I should say there's nothing magic about 3 components. Right? You could just as well have n for maybe n is 4, because this is the one that gets all the attention, right? CW, where x, y, z, and w are each individually elements in R. And of course, there's nothing to stop you from going higher and higher and higher. Here, just makes for longer and longer vectors. So we synthesize all of this together. Yeah, Anders, thank you so much for stopping by. And if you were going to try to axiomatize it, you might come up with something like this. Okay. And it's sort of nightmarish to look at, but move this down slightly so we can actually see the entire thing. But when you start digging into it, it's not so bad, right? All this is saying is that we have these structures, right? We have a notion of addition, so we can add 2 vectors together. We can also scale the vectors. So we can take a vector, something in V, and multiply it by something in R. And just like in the group setting, everything has to satisfy some axioms. Why are the arrows squiggly? I don't know. So I think this one I really don't think is standard notation. But it is notation that Artin likes a lot. So Artin distinguishes between just like everyone else distinguishes between actions, or I guess so a function sends the sends the domain to the codomain, and that he uses sort of the arrows. But when he wants to actually talk about an element in the domain, sorry, let me try to use a neutral color here. An element in the domain, an x value and a y value, then he uses the squiggly arrow to make that distinction. More traditional notation would be it's still an arrow, but it has that little vertical bar at the front. I don't dislike this, the choice to use the squiggly arrows. It's makes it clear at a glance which one you're looking at. So if we start digging into these axioms, then we have the first axiom is about addition, and it says that the things in abelian group, so great news. All of our group story is going to come along for the ride. It is abelian, right? So a lot of stuff is going to simplify. Every subgroup is normal, for instance, which, as you might imagine, based on what we've just been spending the entire last hour and a half talking about, is kind of a big deal. In fact, the deal is even bigger than that, but we'll try to conclude on that point. And then there's some conversation here about multiplication and how it's supposed to work. And I don't want to belabor this too much, but one thing I do want to note is that there's these real numbers here, and we can do lots of stuff with real numbers, right? So for instance, we can multiply two real numbers together, and you could ask, well, after you multiply the two real numbers together, does that have any relationship to what happens if you first multiply a real number and then multiply another one? Right? Sorry, that was a very badly phrased. Let me try that again. So on the right-hand side of this equation, we are first scaling the vector b, sorry, the vector v by the scalar b. Unfortunate name, but there we are. And then bv is a new vector, and we're going to scale that by a. On the right-hand side, we only do one scaling. We scale the vector v by the number a times b. And what this axiom says is that those two things can't be different, which makes a lot of sense. Right? This is what you should want. It is some sort of analogy of, some sort of analog of associativity, right? In the group setting, we had that a times b times c is equal to a times b times c. And you notice that's exactly how the parentheses fall here. It's just a little bit more complicated because before there was only one operation, right? Both of those dots were the same. But in this vector space context, this first dot here is a different operation than the other three dots. The difference between multiplying real numbers compared to compared to scaling vectors. And that distinction shows up again down in number 4, where we see here, this is addition of scalars, oh, excuse me, yeah, addition of real numbers, whereas this is addition is red. This is addition of vectors. And similarly, these are also both additions of vectors. I don't want to spend too much time here because the sort of short version of these axioms is kind of works like you think it should, right? If I tell you that if I have a bunch of objects that I can add together and that I can multiply by real numbers, you would probably guess that all of these things have to be true. And in fact, if I gave you something where one of them failed, you probably would feel a little bit icky about calling that thing a multiplication, right? Or an addition. One point that maybe is worth saying is that it is occasionally useful to be careful about what you mean by the symbol 0, right? So if it needs to be emphasized, the distinction between the vector 0 and the real number 0, we'll put a sub, or Artin will put a sub v, I will put a vector on top of the 0. And in general, if I want to like emphasize that something is part of a vector space, it's common to either put a vector symbol above it, little vector hat, or to bold it, but that's really awkward to do in handwriting. So all three of these notations might get used. This will not be that important most of the time, but it does happen. So I want to give some examples. Um, so the first one is I'll repeat the uh, example from before. I'm not gonna, well, sure, let me number them. Um, so Rn, right, which again is, in real generality this time for, excuse me, xi is a real number. Special case of this, uh, I'm going to I'm going to allow n to be any number bigger than or equal to 0. And you might wonder, oh, wait, hold on, how does 0 work? So we take the convention that um, R0 is equal to the vector space that only contains the identity element. Easy, somewhat boring exercise. Check that this satisfies the axioms. Okay. Um, okay, it sort of feels like it should because the notation is very good. It feels like, if you add 0 to itself, you probably should get 0. If you multiply 0 uh, by a number, you probably should get 0 again, but you can argue this concretely. So okay, that's just lists of numbers. Or anything else besides just lists of numbers? Sure. So a very important vector space is this one, which is the notation we use for polynomials with in X with real coefficients. And so that, remember, a polynomial is a number times a linear term times a quadratic term. Okay, and it can keep going for a while, but it does eventually have to stop. So that's a perfectly good vector space. If I add two polynomials together, it's going to change the coefficients, of course, but um, it's not going to fundamentally change u from being a polynomial. You'll still have well-defined notions of constant, linear, quadratic terms, etc. Okay. Um, we could get a little bit wild here. Okay, so for polynomial purposes, it's important that this stops, but for vector space purposes, it's not. Right? So also talk about formal power series. Again, with real coefficients. Sure. And so this would be something like, it's exactly the same story, except it doesn't end. You still can't stop me from adding two things together. You still can't stop me from scaling everything. And in fact, somehow 3 gives the game away a little bit, right? This, because this Rx sure looks a lot like the first example, except that instead of having a tuple that finishes, we have just a tuple that keeps going forever. But that brings kind of an interesting point, which is that there are, of course, formal power series that don't stop and therefore are not polynomials. So this one's worth thinking about a little bit. Um, and this is very much for your own time, but um, not at all relevant for the direction that we're going. But somehow these polynomials live in this weird space between that's bigger than any Rn, because the polynomial can be as long as you want. It's not just a fixed size, but it's not quite infinite, right? You can't quite go all the way up to formal power series. Um, so for trying to fit it into this scale or this scale, right? It's somehow in the middle there in sort of an interesting way. One last example, although there are of course plenty more, is if you've taken a course in differential equations or have just sort of have a general sense of these things. Um, if I write down any linear differential equation, it doesn't even have to be constant coefficient. Uh, as long as it's homogeneous, and this part actually is important, then this also turns out to be a vector space. Why? Well, you can think about how derivatives work. If you take a solution to that differential equation and you uh, add it to another one, then it's going to be some function. And when you take its derivative, add it to 3 times, or take a second derivative, add it to 3 times its derivative, and add that to 2 times sine x times the thing, well, you can use the fact that the two individual things satisfy this equation to show that the sum does. And perhaps easier to see is that if you scale it, so you just multiply y by c, that's just going to factor a c out of the entire left-hand side, but the left-hand side is equal to 0. So c times 0 is also 0, and you're just as good. Now, I hope that the last one feels different. Like I did spend a little while talking about it, maybe trying to justify it to you, right? Um, it feels like there's some sort of difference between what's going on in the top three and what's going on in the bottom one. And not just because there's some calculus involved, but it's really like it feels like I haven't like told it to you in the way that you might want to hear it, right? Um, so what Artin is doing for the remainder of section 3.3 is going through and very carefully formalizing the concept of what it means to understand a vector space in the way you want it, right? This precisely means that you're trying to come up with a basis. So these first 3 vector spaces, I would say, come with a natural basis. Sometimes people call it the standard basis. I say sometimes, that's a very normal name. People often call it the standard basis. um, whereas the last vector space might have a basis. It does, in fact, but um, it doesn't sort of come with one. There's nothing naturally sort of there in the definition that says like, oh, I could probably use these things to construct the entire vector. Um, Vin, that's a great question, and I'm going to address it right after the right after the lecture, since I want to wrap up quick. Um, so I don't think we're going to have time to talk in any detail about bases, but can I give you one of the big highlights? So there's sort of 2 slogans with um, I don't think I want to actually. I think will be a little bit rushed and it won't be super satisfying. But just to give you a preview of what's coming, there's sort of 2 directions that are coming up in the next 2 sections. One is to talk about bases. It's a basis is a linearly independent set that spans. So in order to define a basis, I need to tell you what a linearly independent set is, and I need to tell you what spanning means. So those are sort of natural objects that you might define for any vector space, even sort of weird things like this last example. And a basis, right, is precisely something that is both. So in some sense, we'll recognize those as being dichotomous. Like it's uh, some sense it's easy for small things to be independent. It's easy for large things to span, and so a basis is that precise meeting ground in the middle. And the other thing is throughout this entire explanation, throughout this definition of vector spaces, I've been assuming that this thing right here, the thing that we scale by is a real number. There's no reason to do this. You can replace these real numbers by more general objects uh, called fields, and this is what Artin does in section 3.2. Uh, Roughly speaking, everything that is true for the real numbers is also true for fields. So if you ever find yourself getting sort of lost in the abstraction, I would definitely recommend that this is a great place to sort of cut down on one level and say like, okay, instead of thinking about any vector space, I'm just going to think about real vector spaces. This stops being true at some point in lecture 4. I think probably, or excuse me, not lecture 4, in chapter 4. So for right now, we're very safe, and I think that it will come up when it's relevant, sort of where the real distinctions are in the linear algebra theory. But that is all upcoming. Thank you so much for tuning in. Um, I don't know, Mohammed, if you want to make any administrative comments before we dismiss folks.